you to do that. Found it, SpongeBob! Come on!
Wow, that looks painful. What we just saw there in the clip was Sandy challenging SpongeBob to find a hay in a needle stack. Now, the saying really is finding a needle in a haystack, but in either case, that was really not the way to do it. Can you think of a better way of finding a hay in a needle stack or needle in a haystack? Yep, magnets. Let's see if it will work for us. Here, I have a watch glass, and in the watch glass, I have a few needles. And I placed a few pieces of paper in it. So let's see if we could take the needles and separate them from the pieces of paper using our magnet. Wow, that was easy, wasn't it? All the needles were attracted to the magnet. So now I'm able to remove the paper without being stuck by a needle. So, based on that intro, what do you think our topic is today? Our topic today is mixtures and separating techniques. At the end of today, it's my hope that we'll be able to learn 3 objectives. Firstly, to distinguish between solutions, suspensions, and colloids. Second, to identify different types of solutions. And lastly, to apply suitable separation techniques based on differences in properties of the components of a mixture. Now, mixtures and their separation falls under the larger topic of matter. And matter can be broken down into 2 categories: pure substances and mixtures, where pure substances are elements and compounds, elements being copper, gold, carbon, or any of the 118 thereabout elements we can find on the periodic table. And compounds are a mixture of these elements. And then we have mixtures, which can be broken down into 2 categories: homogeneous mixtures and heterogeneous mixtures. Now, what is a mixture? A mixture is formed when 2 or more materials or substances are combined, but not chemically. The substances retain their original properties. They can be separated by physical means. And some of those physical means we are going to investigate and observe being done here today. Here we have some examples of mixtures. Wow, mixtures seem yummy. I can think of some ways to separate these things. Most of them involve my stomach though. All right, so I introduced you to 2 words, homogeneous and heterogeneous. Let's see what these 2 words mean. Let's start with heterogeneous. In a heterogeneous mixture, all components of the mixture are visible. This is because they do not combine uniformly. Particles do not are not distributed evenly. All right, some examples would include trail mix, vegetable soup, oil and water, and some medicines. Next, we have homogeneous mixtures. These compounds cannot be distinguished from each other. Their components, rather, cannot be distinguished from each other. They appear as one uniform substance. Particles are distributed evenly throughout. For example, air. In the air, we have have gases like oxygen, nitrogen, noble gases, and all of them mixed together evenly, and alloys, including brass and gold. Next. And in the case of salt in water, what do you think the solute is? Yes, the solute is the sugar. And if the solute is the sugar, what is the solvent? Water. All right? Some examples of solutions include Kool-Aid and soft drinks. Next slide, please. Here is another illustration which shows us that there are different types of solutions. There's gas in gas. We have an example here of oxygen and nitrogen. We all know that the air is 21% oxygen, %78 nitrogen, and 1% other gases, which includes carbon dioxide, water vapor, and noble gases. We also have gas in liquid, and we use these every day, carbonated drinks like our Pepsis and our Buster and our Juicy. Juicy is the best of the three things I just mentioned. Then we have liquid in liquid. For example, wine and vinegar. A solid in a liquid. We just looked at sugar water, which is an example of that. A liquid in a solid. There we have dental fillings and things like that. Then we have a solid and a solid. These include alloys, which would include your brass, which is a mixture of zinc and copper. And here we have steel, carbon and iron, and also 14 karat gold, which is a mixture of gold and silver. Next slide, please. Let's now look at colloids. Colloids are heterogeneous mixtures. The particles mixed in the main components are between 1 to 100 nanometers in diameter. Due to slightly large particle size, colloids appear cloudy. Although the particles are larger than solutions, they are still small enough that they mix and do not separate upon standing and cannot be separated by filtration. Examples of colloids include milk and whipped cream. Anybody else getting hungry as we speak about mixtures? I'm getting. If all the particles have separated, the liquid may appear clear. If not, the liquid may appear cloudy. The larger particle size are for suspensions to be separated by filtration. We're going to do some filtration here today. An example is muddy water, Italian dressing. Next slide, please. Filtration, sifting or sieving, extraction and evaporation, chromatography, we're going to see some of that today, simple distillation, fractional distillation, crystallization, separating funnel through a porous material such as a type of filter. This works by letting the fluid pass through, but not the solid. Examples of filters include coffee filters. We could use a cloth to do things like that, oil filters, and even sand filters. So let's turn our attention back to filter paper. I've placed the filter paper inside of the funnel. Filter paper comes in circles like this. And so in order to fit into the funnel, we need to shape it via origami. Yes, I'm very good at origami. So there are different ways of doing this. I went ahead and I did something like this earlier. This is fluting. And let's try like a cone. And if I look at the top, I'll see two possible pockets. Either one will do. So I'll stick my finger and open the pocket. And there we have our filter paper perfectly shaped to place in our funnel. All right. Now here I have a beaker. And within this, when creating your funnel into the shape, filter paper in the shape, and placing it in the funnel, it's helpful to moisten the filter paper so that it will stick to the sides of the funnel so that I won't have any of my mixture spilling over the sides and contaminating what comes out in the conical flask. And now I am going to dissolve my salt and sand. Let's give it a little stir. All right. Sorry, I don't know if you can see it, but I'm finding it very difficult to see the salt. I'm just seeing the sand to the bottom. So our salt is being dissolved, leaving our sand, and we can now separate the two using filtration. Let's try that now. Contaminating our filtrates. Oh, let's get to that. Now, when we're filtering, whatever comes out through the filter paper into your collection container, in this case, my conical flask, is called the filtrate. And whatever remains in the filter paper is called our residue. All right, so let's just give it a little. I'm just ensuring that I don't damage the filter paper. So here we have quite a bit of filtrate. And in the interest of time, I'll just pour out. And if we could see, in the bottom of the filter paper, we have some sand. Let me take it out. I'll spread it out here. Ooh. And you can see your sand. So I have successfully separated salt and sand. And that, everyone, is filtration. All right? Back to the slides, please. So here we have a diagram of what we just did. We have our funnel, our filter paper, our mixture. And like I said, the residue remains in the filter paper, and the filtrate would pass through and end up in our collection container. The container we used was a conical flask, but in our diagram we see the collection container there being a beaker. Next slide, please. All right, evaporation. That's another technique. Evaporation allows the liquid to evaporate, leaving the soluble solid behind. Example, heating salt water, the water evaporates and the salt crystals are left behind. So in the case where exactly what we just did, we separated salt and sand by using filtration, and the filtrate would have been salt water. If we wanted to recover that salt, we simply use the technique of evaporation. The water would be evaporated and lost, and we will collect our salt crystals back again. We see this in practice in Union Island. For those Unionites, there's a salt pond, a salt flat in Union, where when the weather is right and the season is right, salt crystals form, and you can go and just pick them up and collect them. Right? And they're very beautiful, large crystals, a lot larger than those that we buy in the supermarket. I think they call it rock salt. Next slide, please. And again. The next technique I want us to look at is chromatography. And in chromatography, we use it to separate dissolved substances in a solution from each other. And we have an example here in front of us. Let's take a look. So here I have two beakers, three rather, set up. We have glass rods, beakers, and we have some strips that we have cut from filter paper. Their porous nature allows them to be very good surfaces to perform chromatography on. I have placed dye food coloring, a drop of food coloring, much like this one here, on each strip of filter paper, and I added a solvent. The solvent I used is a 50-50 mixture of alcohol, 95% alcohol, and water. And this is what became of our chromatography. We see that blue and red haven't really separated out. I think that's because they are primary colors. All right? But the one in the middle, they started out as green. Hopefully that's not too much. And let's see it at work. Very good. So there we see the solvent rising up the filter paper by capillary action, adhesion, cohesion. And the solvent is now going to separate. All right, so if we leave it for half an hour, it'll turn the beaker on the, this is my right, your left perhaps, is how this green pigment will end up in about half an hour. We could probably come back and look at it later. All right, chemistry is awesome. Science is awesome. Next slide, please. I want to talk about separating funnels. Separating funnels. Explore. Awesome, that was fun. Now, the next technique I want us to look at is the use of separating funnels. A separating funnel can be used to separate mixtures of two immiscible liquids, that is, liquids that do not mix together to form a homogeneous solution. When such a mixture is allowed to settle, the less dense liquid will form a layer on top of the more dense liquid. An oil-water mixture would be an example of this. So here we have in front of us our separating funnel. We have here a retort stand a clamp stand, our separating funnel, and for our collection container, we have again a conical flask. In our separating funnel, I have placed oil and water. I dyed the water blue so we could clearly see it a bit more easily, a bit easier. Right? So it would have settled out again, but I might just be able to give it a little whirl and see how immiscible liquids work. So I shake it up. There are two immiscible liquids. All right? And even after shaking it up thoroughly, they still separate out. So this is an example of what? What mixture we know settles out when left to stand? A suspension. So this is an example of a suspension. And as we see here, the oil, which is the lighter of the two, floats to the top, and the water, which is the denser of the two, remains at the bottom. So with this instrument, so it is much easier and safer to separate using this technique. So if you look down in the conical flask, as the water drains out, and we're going to see if we can separate the water from the oil. Look at this. All right, it's getting close. You see that it's getting close? It's going to be at the ready in our separating funnel. All right, so that's how we use a separating funnel. So next slide, please. So here again, we have a diagram. All right, so this is magnetism, and we looked at it a little earlier. So magnets separation is a specialized method used for separating magnetic material, like the needles that SpongeBob so easily swam through. So magnetic material include things like iron from non-magnetic materials such as soil and plastics. It is commonly used in mining and recycling. Okay, next slide please. And we see it here at work. Next slide please. Before that. something that looks like this thing above. Oh, that was even more fun than the last time. All right, so the next separating technique is distillation. So distillation is similar to evaporation, except that the evaporated substance is retained after being heated. The vapor of the evaporated substance then passes through a tube known as a condenser. The gas is cooled, using it to condense back to a liquid so that it can be collected. The liquid collected during distillation is called the distillate. Distillation can be used to separate liquids based on their different boiling points. Distillation is commonly used in producing petrol, alcohol, and perfumes. It can also be used to remove dissolved impurities from substances, such as the purification of water. All right? And so here in front of us we have a setup for simple distillation. All right? As I'm standing here, I'm even remembering that in the Grenadines, I think it's Myro or Mustique, they are distillation plants that convert salt water into fresh water. So we use distillation here in St. Vincent and Grenadines in many different ways. All right, so let's take a look at this setup. Again, we have our retort stands, our clamp stands. We have our Bunsen burner that's providing the heat, our tripod, and here we have a distillation flask, a round bottom flask, in which we have placed our solution. The solution we have placed in here is a solution of salt and water. I've also added a red dye so we could see what's happening a little more clearly. So we are heating this solution and it is rising up our apparatus. Here we also have a thermometer. The purpose of the thermometer is to measure or keep stock of the temperature so that we don't go too high or too low. And in the case of fractional distillation, it will be even more important as we try to separate substances of different volatilities or boiling points. So the apparatus then leads into our condenser. And our condenser's purpose is to cool the gas back to a liquid. We see condensation every day. If you drink a glass of water and you have ice in it and you rest it down on the table, eventually you'll see beads of water on the side of the glass. And that's an example of condensation, where the water vapor in the air, there is about 0.01% water vapor. The water vapor in the air condenses on the glass, on your cup, because it is cooler than the air around it. So we have here a condensation tube, a condenser. And the way this works is by passing water through it, cool water. If you look here to my right, we see a tube that's hooked up to our pipe. This tube goes to the bottom of the condenser here. So water circulates and goes into this other tube, and we empty it into the sink. All right? And in that way, cooled water is also always circulating in the condenser and thus is condensing the gas, cooling the gas, the water vapor, back to liquid water. And then we have a spout here that is directing, and we could see the water dripping as it has condensed within our condenser. I get so excited just even looking at this thing. Science is really awesome, I swear. All right, so we have here an example of distillation at work. And so in places like the Grenadines, where water is scarce, rain is scarce, a distillation plant can be set up where salt water can be heated, the vapor of water vapor collected and stored in tanks. And if needs be, it could be further purified. I don't think you probably need to. But it could be further purified to make portable for tap water. So distillation at its best. All right, next slide, please. All right, so here we have our water, the inlet at the top. It's our condenser, sorry, the inlet at the top. Water out at the bottom. So that those two ports will be used to cool the condenser. We have our round bottom flask, which will be heated using our Bunsen burner. Our mixture will be heated. And in our case, the water turns to water vapor, rises, finds its way into the condenser where it turns from water vapor back to water and then collected in a conical flask. And what's collected is called the distillate. Again, we use this technique to make alcohol. So Sunset, we use it to make perfumes, and we use it to purify things like salt water to make it possible. Next slide, please. The last slide, please. All right, cool. So we have almost come to the end of our session together. And so we're going to do a little activity that will help us to see how much we have learned. And so at the bottom of our screen, we have a few pictures, a few items. And interestingly enough, most of those things are very edible. Again, oh my gosh, this whole topic making me hungry. I need to go get something to eat. So let's start with any of them. Let's pick one. And we'll place them, or place the mixture in the correct circle. We have 3 circles. One representing solutions, one representing colloids, and suspensions. So our solutions, colloids, and suspensions. Let's do a little recap, understanding that these are all mixtures. Solution there being a homogeneous mixture. Evenly distributed. Colloids and suspensions are heterogeneous. Mixtures, they can be separated. They are not evenly distributed, rather. And suspensions in particular will settle out when left to stand. So let's pick one. Anyone at random? Let's pick that. Yes. What does this look like? Looks like medicine. And for those of us who would normally visit the pharmacy to collect medicines, we will see the pharmacist taking water and some powder and mixing it in a bottle and to create this liquid for us to use. So where would this liquid go? Is it a solution, a colloid, or a suspension? Let's see if we could use our knowledge of medicines to see if we could solve this problem. I think that on one of these bottles I saw shake well before use. Have you ever seen that? Yes. So if we have to shake well before use, that means milk. Ooh, yummy, I think. Yummy with cornflakes, yeah, with cornflakes. So let's use our knowledge of suspensions, colloids, and solutions to see if we can solve this one. Is milk a suspension, a colloid, or a solution? When we pass light through it, does the light come out clear or is it cloudy? It's cloudy. It's actually milky. So, since milk is cloudy, is it a suspension, a colloid, or a solution? It's a colloid. Excellent. So let's place it in the colloid circle. Nice. Next. Here we have a cup. And if we enlarge this cup, we'll see that at the bottom we have honey. Then we have some beverage, followed by dish liquid, followed by colored water, followed by oil. All right? So it's about 4 or 5 immiscible liquids. So they're immiscible, meaning they can fall, the denser one will fall to the bottom. So using that piece of information, is it a solution, a colloid, or a suspension? It's a suspension. Exactly. Because when left to stand, it will settle out. Next. We have vinegar. I can remember calling vinegar or saying the word vinegar in my presentation. Under what mixture was it said? It's clear, I could see through it. And if I shine light through it, it'll pass through real easy. So it must be a solution. Vinegar is a solution. Excellent. What do we have next? No, I don't drink tea. But I could see people drinking it. Seems healthy. Now, we're not looking at the tea bag. Let's just look at the tea after you have drawn it. It's clear. I can't ever remember tea being cloudy. And if I leave it to stand, it's not going to settle out. So tea must be a solution. Tea is a solution. What do we have next? What do we have next? We have clouds, oh my God. Yee, ooh, this is an outlier. This looks nothing like any of the things we've seen before. Now, clouds are mixtures. Let us see what it is. Can I see through it clearly? No. Do they settle out? No, they're just up there floating away without any care in the world. If you pass light through it, is it cloudy? Yeah, you see that there? It's cloudy. It's a cloud. Therefore, it's a colloid. Clouds are colloids. Excellent. Then we have perfume. Perfumes are solutions. That's a pretty easy one. Let's see what we have next. Ice cream. Ice creams are nice. Again, really hungry. So ice creams are also mixtures. And in this case, it's a colloid. Next, we have throughout. So therefore, based on the fact that I have to shake it up and it settles out, salad dressing, Italian salad dressing must be a very good suspension. Our tech man got it locked. And even bubbles, which should have indicated A. So if it settles out, that means mud must be a suspension. Wow. Our tech guy got it locked. Next, we have a Kool-Aid jammer. All right? Something we drink. It's a mixture of sugars and flavors and dyes, all in some water. And it does not settle out, and it's pretty clearish. So it must be a solution. So, Kool-Aid, soft drinks, juice, solution. So here we have it. Mixtures and the techniques to separate them. Thank you so very much for being here with us today. I hope you have learned and have had fun. Until next time, my name is Andrew De Silva, signing off.